just to say before I did another test. Oh, okay. So I ran the problem with not the problem, but one of the issues with the on small numbers of nodes, the halo swapping. A lot of your, we'll actually talk about this in this lecture, but a lot of your neighbors are often on the same node, potentially, and so you don't maybe have as many off-node messages over the network as you thought. But I was able to run, surprisingly, a test on hopefully this ran on 65,000 processors. This was 512 nodes, and so this is give you sort of really big a big run. This went through pretty quickly, surprise. So actually on ARCHER2, although running a job on a big job on 512 nodes, which is 10% of the system, would be queued for a long time, a short job can run quite quickly, because if Slurm is trying to schedule a 1024 node job, it will start draining the system. So there might be 512 nodes free only for a short time. So because I said I only wanted to run for a few minutes, it ran very quickly. And what can we see is that send receive again really is very bad. 132, that's really quite bad. Oh, I'm doing 1,000 doubles. Oh, so I did this the wrong way around. I meant to do anyway, but it's still 1,000. I meant to do 1,000 and 10,000 anyway. Sorry. But anyway, there we go. We can still see some reasonable numbers. So red. Sorry, I've gone this. Send receive is bad. So I said I don't like send receive for pedagogical reasons. It also shows that it doesn't perform that well. Red black is, so these pairwise ones gave me 300. So you know the benefit for the wait all is less than we saw before, but it is still significant. It's still about 20% faster, which isn't bad. And then these other ones are actually, oh, there we go. And this could be, I mean, I would need to rerun these because on large process counts where you're using significant fractions of the machine, you're also significantly sharing the network with other users. So these will be more variable, but there's still a significant improvement for, you know, low 300s for pairwise swapping and getting up to 400 for these other more, I would say, global operations. So that was just something I was playing around with. I will now get the actual talk up, which is here. I'll go through this. It should run about half an hour, and then we've got some time to I'll explain a bit about tomorrow. So first, we're going to review topologies in MPI. You may have used them if you've been on the introductory course that the EPCC teaches, that we teach. You'll have seen Cartesian topologies, but you won't have seen graph topologies. So I'll cover those. But as MPI3 added these new neighborhood collective operations, I've spelled them in the UK. Whoops. In the UK way, but they're spelled in the American way. MPI neighbor, all gather, and all gather V. I'll explain how these work. But as I said, my go-to use case is a Halo exchange we done with a single MPI communication call. Now, this is a comment actually for our MSc students for placeholder point, but I do have an example code for tomorrow which has point-to-point Halo communication, and you could replace it with a single MPI neighbor all to all. So topologies, on a standard case, we have a 2D domain decomposition of an L by L array. We split it up into P subdomains where Px times Py equals P. So we have subdomains of size L over Px times L over Py. So for example, we might have a 100 by 100 array on 8 processes, and we might split that into a 4 by 2 grid where we have 25 by 50 arrays on each process, and we would have halos on those because So the important point is nearest neighbor interaction implies nearest neighbor comms. And so as well as you have a 2D grid of px times py processes, and that's the grid in which you will be communicating. Now, if you just do point-to-point MPI, then well, I'll come back to that. Sorry. And the second, so you will have covered these if you've done the EPC. Also, that's a structured case. We have a very, very structured case. However, there is also support in MPI for unstructured problems. If any of you have ever done any engineering problems, finite elements or such like, what happens is that you have a much more general domain split into. So the important point about this 2D decomposition is that you have a 2D grid resulting into a regular mesh of processes. In a more general situation, you won't have this regular grid. You'll have an unstructured connectivity where every process will be communicating with an arbitrary number of other processes of an arbitrary list. Okay, so it's very simple for the regular case, but if you're doing unstructured problems, then that isn't the case. So what happens here is that if you're doing unstructured mesh has n elements, you split them up into p subdomains, each of n over p elements. Wherever there's neighbor interaction, I should have a diagram here, it implies nearest neighbor communications. But the communications pattern is no longer a regular grid, it's an unstructured graph. Okay, each process communicates with an arbitrary number of neighbors. And you can do things, so you end up with your communications pattern isn't a regular 2D grid, it's a graph. And you can actually weight that graph, because you might say, so here in this graph, which represents your communication structure, the nodes are your MPI processes, and your edges represent communication between processes. And you could weight it you could weight the vertices to represent communication cost, computation cost, or the edges to do communications load. For communication patterns, these graphs are typically undirected, because if A communicates with B, then B, for neighbor exchange, if A communicates with B, then B communicates with A. But though, so there are two communication structures you might want to use in MPI. One is a regular grid, but the most general case is an unstructured a graph. And so if you want to test, so the important point is in MPI com world, every process just has a number, but MPI knows nothing about the distribution of them. So the idea here is you actually tell MPI, look, I know you think MPI com world's got 256 processes in them, but actually I'm thinking they're being arranged in a 60 by 16 grid. And so if you've got a Cartesian topology, that's called MPI cart create. If you want to say these 256 processes are communicating in a general graph topology, you do MPI graph create. The original graph creation routine was not scalable, and so because every process had to specify all edges in the graph, but the general ones are MPI dist graph create adjacent, rather a mouthful. But what happens here is it's the natural thing. What you say is each process tells MPI what their incoming and outgoing neighbors are. You basically say, look, I will be communicating with all these people, and then MPI creates the global, well, it then understands what the global connectivity is. There's also MPI dist graph create, which is distributed, but in dist graph create adjacent, you say who your neighbors are. In MPI dist graph create, anybody can tell who the neighbors are. I don't really understand why they've put that in there, but it's not. So what can you do with these once you've done them? Well, you can ask a topology. You can say, what kind of topology are you? Are you a graph topology? So what I should say, when you create a new communicator, I should show you the example. That's why I had this code up before. Let's show you the example, which will be much more illustrative than just chatting. Like, sorry, I've lost my, as ever, I've lost my windows here. Sorry for the delay. So no, it's in the Halo bench, sorry. So what we do, I'll just show you the call. So what we do is we say to MPI, I'd like to create a Cartesian topology, and you give it a communicator as an input, and this is that's actually MPI com world. Sorry, there was a question here. Oh, that's it. I'll come back to that. I'll come back to that, Mark. That's a very good question. So the topology construction starts. So this says I've got an input communicator which is MPI com world. I've just set it out the way. I want it to be here. What I want to do is I'm telling MPI this is now arranged into a 3D grid. End dim is 3. Dims are the sizes. So when we had that tells it how they should be split up. Periods tells it if a dimension is periodic or not, whether your neighbor wraps around. And this reorder I'll come back to, but reorder equals false. If reorder equals true, MPI is allowed to have your what you get back is a new communicator called cart.com. So this is an input, which is MPI com world. This is the output cart.com, which is got these dimensions. Okay. Reorder, if reorder is false, then your rank in cart.com is the same as your rank in com. If reorder is true, then you might have a different rank in cart.com from com. I'll explain why that might be useful later on. However, having created the Cartesian topology, you can then do various things with it. And for a Cartesian topology, what you want to know is who are your neighbors. And within this Halo swap routine, you'll see it's called com data. But the important one is that basically this routine MPI cart shift says I loop over all the dimensions, that's X, Y, Z, and I say in that dimension, who's my neighbor down and who's my neighbor up. Now you could do all this yourself, it's just a bit of bookkeeping, but the nice thing about, but at least in this instance, what the neighbor, when I do this cart shift, it respects the periodicity. So if the topology is periodic in that dimension, it will give you a wraparound. If not, it won't. However, there's not an enormous amount of advantage here. You've gone to all this effort of setting up a Cartesian topology, but all you're doing then is working out who your neighbors are. And when you actually do send and receive, you still send to a particular rank. And if you're going to do the same for graph topologies, it's kind of even less useful, because on input you have to tell MPI who all your neighbors are and how many there are, and the only thing you can inquire from them is who all your neighbors are and how many there are. So it doesn't. They basically introduced topologies very early on in MPI, but didn't really exploit them to their advantage. What you would want to be able to say, even though you can tell MPI what the structure of your communications is, when you actually send and receive messages, you still have to say just to MPI send, MPI receive to this neighbor from this neighbor. And all the topologies do is give you a convenient way of doing the bookkeeping. The neighborhood collectors take that to the next level. You can just say send and receive messages from all my neighbors, and that means that they suddenly become a lot more useful. So there was a question here from Martin about work with GPU accelerators. So that's a very good question. So what might you want to do? What would be special about the accelerator? So in the naive way of programming MPI on accelerators, all your MPI processes are CPU. All your MPI ranks are CPU processes, and it just happens that when they do communication, they're able to offload onto the GPU. So until a couple of years ago, to MPI, an MPI program running on a GPU system was no different. It was just a bunch of MPI processes running on a bunch of CPUs doing communication with each other. And so all the MPI ranks were CPU processes. And as I said, it just happened to be that every now and again they might go a bit faster because they could offload the GPU. Now, I know that now you can do at least certain MPI calls on the GPU. Is that correct? So so what's your question? What might you want to be able to do with them? I didn't quite understand. It's a good question. I didn't quite understand exactly what you meant. Would you want to be able to differentiate between who is a GPU process and who is a CPU process, or something different? Martin, I don't know. Sorry, I may not have understood your question correctly. I'm not sure if I don't actually understand. So I don't quite understand your question, because there are issues around CPUs and GPUs, but we'll maybe come back to that. So the nice thing about in the Cartesian topology, you can do MPI cuts if you're my neighbors. In the graph topology, you say how many neighbors do I have? Who are they? Find out neighbor or any process. Yeah, you can basically inquire how many neighbors do I have and who are they? So here's an example which I just found somewhere. So create a graph topology. So MPI all gather is a routine where every process gathers data from every other process. MPI neighbor all gather is a routine where every process gathers data from its neighbors. Who are its neighbors? They're the one that it's connected to in this. This is a general example of a graph where rank 0 is connected with rank 1 and rank 3. It has a bidirectional link to both, just to make things complicated. Rank 2 communicates with rank 1, but rank 1 not with rank 2. And so this is a code which creates that. So basically, you have to specify a whole bunch of stuff. But basically, the ranks specify how many neighbors they have, the degree is, and who they are. Okay, so rank 0 has 2 neighbors, and they're 1 and 3. Is that what we expect? Rank 0 has 2 neighbors, 1 and 3. These are outgoing neighbors. And rank 2 has 3 neighbors, 3, 0, and 1. Is that right? Rank 2 has 3 neighbors, 3, 0, and 1. So this setup routine here creates that previous that topology there. And then what we do, this is the setup for it, and we do MPI dist graph create. We say these are the sources. No, that's sorry. That's my rank. I specify what the number, the degree, the destination. There's optional weights for these, and then you get back a graph topology. And then you can do an MPI neighbor all gather, and that gathers. So what happens there is you gather from your neighbors. So rank 2 would only gather from 1 and 3 and 0. Yeah. So it's a slightly contrived example, but again, it's important to note that these just generalize the normal routines, and in something like an MPI all gather, all meant everybody. An MPI neighbor all gather means just your neighbors, and that can mean if you're in the Cartesian topology, that would mean your 6 neighbors up, down, left, right in the 6 directions. So as I said, reorder equals true enables remapping of processes. Why might you want to do that? Well, you might want to minimize the number of inter-node communications over the network. So again, in the early days of MPI, I used to play around with this, and most MPI libraries either didn't do this or didn't do a very good job. But at least in principle, this is so for the reason when you run an MPI program, there'll be some default mapping of processes to nodes, and that is just on ARCHER2 is just straightforward. The first 128 ranks go on the first node, the next 128 on the next second, the next 128 on the third until it runs out, unless you do some playing around. Now, that might not be optimal for communications, but since MPI doesn't know anything about your communications pattern, how can it do anything better? Once you've told MPI what your communications pattern is, you might say, my processes are in a 3D grid, they're all communicating with their neighbors up, down, left, right, forward, backward. MPI might be able to, well, actually, that means that the location of your MPI process is not optimal. So, for example, I've got an example here. I've got 256 MPI processes on 4 nodes, and I imagined that each node has 64 CPU cores. So almost all systems have a default allocation where the first 64 ranks are on node 0, the next 64 on node 1, but this may not be optimal. So for example, if we have, we've got a 64 by 1024 array, okay, which is quite skewed. And what we say is we want to split that into a Cartesian communicator. Sorry, we want to split that across 256 MPI processors. Let's choose a 4 by 64 distribution. Okay, so our 64 by 1024 array, which is quite tall and thin, if I draw it like that, we do a 4 by, because that means each local domain is 16 by 16 square, and that might minimize communications. That means the layout is like this. So node 0 has ranks 0 to 63, node 1 has ranks 64 to 127. You'll see that every single communication in this first dimension is internode, goes across the network. Each process communicates with its 4 nearest neighbors. A total of 128 messages are sent over the network from each node. That is, every time you send a message left or a message right here, it goes over the network. So 128 messages sent over the network. That is not an optimal thing to do. And so what you could do, it's a bit difficult to draw, but you could map it like this, so that node 0, node 0 has a different distribution, and you have only 8 messages per node over the network, because it's only these guys up and down the way. So I took a bit of difficulty to draw this diagram, but the important point is that the default distribution of processes to physical processors on physical nodes may not be optimal, and by changing the way that the ranks are numbered, you might end up with a distribution which optimizes communications, and optimal communications almost inevitably means fewer messages sent over the interconnect, because that's slower than going internode. And so you can set reorder equals true, MPI does something sensible, or you can do it by hand. But that's an interesting point of how well MPI does it. Oh, sorry, that's the ranking con world. Yeah, sorry, I should have said. Now, this is just a logical change of rank. It just says that, rank 2 in ComCart, rank 60 in ComWorld becomes rank 2 in ComCart. That's all this is saying. 60 is swapped with 2. It's just a logical reordering. It doesn't move the data, and so that can be a real problem. You might have to exchange data between new and old ranks. It's sometimes easier to do this at launch time, rather than launching the application with the default distribution of ranks to processors and then messing around with it internally. You can actually, if you know your Slurm parameters a lot, mess around with how that they're allocated. And so it is possible when you launch a Slurm job to say, I want this ranked. So that is maybe easier to do, and there are tools that can help. So, the ARCHER2 perf tools, if you run a program, it can monitor the communications and actually say, actually, I think that your program would run faster with this distribution of processes to physical processors. And if you're lucky, I think it even gives you the Slurm incantation to do that. So this is a complete freebie. In other words, you don't need to rewrite your program. All you're saying is at launch time, the mapping of MPI processes to physical nodes and processors is non-default. And the ARCHER2 perf tools can actually help you with that. I haven't looked at that for a while, I have to say. So just to give you the neighborhood collectives, they're in these sections. There are non-blocking versions, and there's an example. So the important point is MPI neighbor all gather sends the same piece of data to all neighbors and gathers one piece of data from each neighbor. Okay? So you're gathering. That's typically not what you want to do. If you want to do halo swap, you want to send different data to each neighbor, the up halo to the up neighbor, the down halo to the down neighbor, and you want to receive different data from each neighbor. So actually, the MPI neighbor all to all is the one you want to use. Now there are MPI neighbor all to all V, and all to all W. So These are slightly, have I gone through the gory details or have I just, yeah, okay. The use case is regular domain decompositions where the decomposition is static or changes infrequently because creating topology takes time. Now, the syntax of these gets quite tricky for various reasons, but I'll go through them. You'll probably have to, if you want to use these, it'll take a bit of head scratching. But I'm going to use all tools. So MPI neighbor all gather sends the same send buffer for each outgoing neighbor. So you have one send type and one send count, and then all the other neighbors gather contiguous chunks in receive buffer from each incoming neighbor. So basically, I receive different data from different neighbors into contiguous chunks. That is often not useful because, as we keep saying, the important point about Halo data is it's often non-contiguous in memory, it's strided. And so MPI all gather V is a slight generalization that allows you to set, but it still has it allows you to change the send count and the chunks can be non-contiguous. It doesn't really solve all your problems, to be honest, because it requires a global send type and a send count. So you're basically sending and receiving the same data. Apologies, you're sending the same data to everybody. So MPI neighbor all to all is the communications pattern we want for Halo exchange. You send different data to your different neighbors and receive different data from your different neighbors. But there's a global receive type, send count, receive type, and receive count. And that is not going to work because we know in a boundary swap that the different halos have different types. One might be contiguous, one might be strided in one way, might be strided in another way. And so you need to be able to specify an array of send types and an array of send counts as well, and an array of receive types and an array of receive counts. And that is the one you want to use is MPI neighbor all to all W. All to all V stands for V, where allows you to vary the counts but not the types. So this is general enough. So it's all a bit about, you maybe need to look at it all. But MPI neighbor all to all W is the routine which you can use for Halo swapping. Non-contiguous variable size chunks in send buffer for each outgoing neighbor. You have an array of send counts, send displacements, which is where the data comes from, but most importantly, an array of send types. So for each of these, you would specify what the Halo type is, be they your contiguous types, your vectors. And so the syntax is pretty complicated, but it does allow you to do Halo swapping in a single call. So for example, this is a diagram where we want to do Halo swapping in 2 dimensions with MPI neighbor all to all W. We're going to define MPI data types for all the halos. So the send counts are all 1 because we're only sending and receiving one halo. That doesn't mean we're sending and receiving one data item because the halos themselves are our data types. Okay, so we have a send buff here. We have the way I've drawn it here with I going down and J going on. This is that these 2 halos are contiguous, and so we've got the 0th and 1st send types are contiguous types, but the other, I'm not doing this very well. Yes, the other 2 types are vector types. So in the 2nd dimension, the send types 2 and 3 are vector types. We then have to compute the displacements, which is where the data starting point, which is slightly confusing, and we have to compute it in bytes. So there's a lot of setup to do, but you only do it once, and once you've done that, your actual send receive call is very, your actual Halo swapping call is very, very compact in this. So you'll need to sit down and draw lots of pictures and such like, but having defined it, it's quite easy to use. But the important point is that to make practical use of neighborhood collectives, you will typically need to use MPI derived types because you will need to be able to send, you will want to send non-contiguous data in at least 1 or 2 of the other dimensions. and the all-to-wall and all-to-wall V only allow you to send contiguous data. And sorry, only allow you to have a single data type. Apologies. Here you need multiple data types. So it's slightly and the receive buffers point to different places as well. So it is slightly confusing potentially, but they probably are worth looking into. And that's an example for a Cartesian communicator, as we have in the benchmark, but it generalizes to a graph type communicator where all these numbers are where the neighbors will be each process will have different numbers of neighbors, and so again the neighbors here it's the same call, MPI neighbor all to all, regardless of whether you have a graph topology or a Cartesian topology. All it means is the neighbors are computed differently in the two cases. In a Cartesian topology, it's just up, down, left, right, and all the dimensions. In the graph topology, it will be different on each process. We'll have an explicit list of who its neighbors are. So that was it's a bit of a run through, but it's really just to point there is useful for irregular domain decompositions, where the decomposition is static or changes infrequently. That's because every communications pattern requires you to create a new topology. So you don't want to change it too quickly. You can investigate replacement points for communication with Halo Exchange. With neighborhood, you can replace Halo Exchange by point-to-point with neighborhoods, and you probably want MPI neighbor all-to-all W. There is also a non-blocking version. So in principle, MPI can optimize the whole pattern of messages, and so your application code is simpler and easier to read. So I mean, that was a bit of a run through. I know people wanted to know about neighborhood collectives, but they are. The important point is that when you say all in a neighborhood collective, in a normal collective, all means everybody, all P processes. In a neighborhood collective, all means all your neighbors, and who your neighbors are inferred from the topology you provide, and that topology is a new communicator, which can either be structured, Cartesian communicator, or an unstructured graph, which you create with these graph routines. So it's slightly yes, it's slightly what am I trying to say? It's slightly technical and complicated, but it is probably worth looking into. So I'm sorry that lecture maybe not as clear as it should have been, but I don't know if I had any questions on that. Sort of at the end, near the end of the day, but I mean, if we look at my code, sorry. So bench is simpler than it would be in reality, because I'm not worried about having non-contiguous data. But if you look at the routine, which does this general one, this does the weight all. Well, you'll see all I do with the Cartesian communicator is to compute my neighbors. Call com data gives me back who my neighbors are. The actual send and receives are just normal send and receives to a particular neighbor. However, in the collective, in the neighborhood collective version, it is actually if it's down at the bottom here, it is literally send buff and everything else is effectively hidden away in CART-COM. So it is deceptively simple. All there's a lot of setup to do. That's a very good question. No, so, well, you have a choice. So, for example, if you want to do an all reduce, if you did an all reduce on the COM-CART or COM-world, you get the same answer, modular rounding errors. It would. So that is a choice for you. it's a philosophical choice. You could do so. You have to use the topology communicators for the neighborhood exchange, but you could use them everywhere because they contain all the processes. So for things like all reducers and stuff, you can call them on either, and you will get the same answer. As I said, modular rounding errors, because it might do them in a different order possibly. But does that answer your question? So it's kind of a philosophical question, actually. Do you say, I forget my world com, or do you say, I will, yeah. But it's just, it's important that all these, if you called an all reduce on a graph topology, it would just ignore all that thing and say, well, all I care about this topology is who are the members. I have to say, though, things like reduction operations might be quicker on COM world, because the library might do a quick check, because clearly, you know, if you do a reduction operation on a general communicator, that in general could be a subset of the whole communicator. So it might have to do something special. If you do a reduction operation on COM world, it's kind of all, you know, that's easier. So some of the, I maybe should look at some of the library teams may say, you know, if COM equals COM world, then do a simple thing, else I have to do a bit more work to work out what the heck's going on here. So I would say for performance, it might be better to do all your other stuff in COM world, possibly for performance reasons. Just thinking, well, it's a bit more explicit what I'm doing here. But it is really a design choice in terms of a philosophical choice in some sense, but there might be some performance implication. There's no specific exercise associated with this, but I do have some suggestions. Well, there is. It follows on from tomorrow, so but if I basically share. So you can see here that the halo edge. So you can look at that to see if you can understand. I do appreciate it's in 4chan. Apologies if that makes it hard to read for people. That's for historical reasons. But also tomorrow's traffic modeling problem sheet contains a final MPI to replace point-to-point boundaries with neighborhood collectives. So if you're interested in that, you could look at that. I will cover the traffic model. So tomorrow, all of the MPI hybrid MPI OpenMP and MPI shared memory and put get routines are based on this, at least the exercise is based on the simple traffic modeling exercise. I will actually spend 5 minutes, 10 minutes tomorrow morning basically explaining the traffic. It's a very, very, very simple model. If you've done the EPCC MPI course, you'll have seen it before. If not, it only takes 5-10 minutes to explain. But I have this actually has a whole bunch of stuff on it, but more than we're going to do here. But it does contain all the exercises we need. So yeah. So appreciate it's been quite a long day. It's very hot actually. I'll be around here for the next 20 minutes. I'm happy to chat to people. I noticed there were some questions people have which maybe aren't going to be covered in the course. Or you might have individual questions about your own code. You might want to show me your code or something. So I'll be around for the next 20 minutes till 5 if you want to chat or ask any questions or play around with the exercises. If not, I'll definitely see you tomorrow at the same time. Tomorrow's timetable is very similar today, except we basically, again, the last session finishes at 3:30, and you know, I'll be around to help people out afterwards. But we'll start at 9:30, and we'll be the formal teaching. Sorry, the lecture will be finished by 3:30 tomorrow, as I certainly, and then we'll have a coffee break. So yeah, speak to you tomorrow. But again, please, if you have any, I don't say off-topic questions which aren't going to be directly answered in this course, then please, I'm happy to chat during any of the practical sessions or such like. No problem at all. But I'll be around for at least the next 20 minutes for you to, if you have any questions, just pop them in chat. And I said we can chat. It doesn't have to be. We can talk. Proper talk, microphone talk, if we just go into a little breakout session. That's easy to set up here. So You won't have to talk by text if you want to chat about anything.